Oh, I figured it out. That's really not a hard thing to figure out. I just had to. I don't know that I've ever used this iPad to look up anything on the internet. I just don't like iPads. So I just use it for school. And I had to do the little. Well, that's not true. I have looked stuff up on an iPad on the internet before, but I have like a keyboard that I attach to it because I can't stand the screen keyboard. I don't even know what you call it. But anyway, I found what I want. Am I still recording? I think I'm still recording. I better be. All right. So exterior angles of a polygon. So here's what they're going to do. Okay. There is a polygon. So we got 1, 2, 3, 4, 5 sides. We've got a pentagon. They've drawn in all the exterior angles. Okay. So what happens is they're going to take, hang on. Let me come back to the notes for just a second. Wait, here's what it is. So the exterior angles of a polygon. Now this one, it does have to be convex, because if it were concave, then there is no exterior angle right here, because the exterior angles get formed when you extend that side out. Okay, so this is the one that, like, this is only good for a convex one. But if you take and just draw in some random convex polygon. Now you have to pick a direction, whether you want to be working your way around clockwise or counterclockwise. But it's kind of like making a pinwheel. Like extend this side and create that angle. There's an exterior angle. So I'm working around clockwise. So I'll extend the next side and look at this angle. That's another exterior angle. I'll extend this one and look at this angle. I'll extend this side and look at this angle, and I'll extend, that kind of got a little crooked, and look at this angle. So I'm looking for, what do those exterior angles, what do their measures all add up to? Okay, so let me see if I can get back over. There it is. Watch this video. It's the coolest way I've ever seen it explained that makes perfect sense. Oh, look, you formed a circle. There's 360 degrees in a circle. Let's watch it again, shall we? Yeah, those exterior angles on a convex polygon, it does not matter how many sides. Oh, that's not what I wanted. Oh, no. Right here, that's what I wanted. It doesn't matter how many sides there are. The sum of the measures of the exterior angles of any convex polygon is 360 degrees. Doesn't matter the sides. So here's some example problems. This is where they start getting super fun. And should we do this? Hang on, before we get to that, I just took a gander at my old notes. And this is probably a good thing to write down. That means that this measure, plus this measure, plus this measure, plus this measure, plus that last one, add up 360 degrees. Okay. Alrighty. So here's some example problems. So a polygon has 32 sides. We could say it's a 32-gon. A, find the sum of the measures of the interior angles. Okay. So the interior angles, if it's got 32 sides, I'm going to create 30 triangles. Because it's always the number of sides minus 2, and then you multiply by 180 degrees. Which, let's see, 3 times 8 is 24, carry the 2, got a couple of zeros. There's 5,400 degrees. Okay, for the B part, what's the sum of the measures of the exterior angles? And when they say one angle at each vertex, that just means, that's where I was talking about how you pick a direction. Like, you don't want to look at this exterior angle and this one at the same time. Like, just one. And here's the beauty of this one. We don't have to do any work because the exterior angles of a convex polygon the measures of them always add up to 360 degrees. Okay. Now, here's some more vocabulary. Polygons can be equiangular or they can be equilateral. So if they're both equiangular and equilateral, then we say they're regular. So equiangular is when you have all the angles are the same size. Equilateral is when all the sides are the same length. When they're both, it's called regular. And this is the part that kind of drives me a little crazy. Like, this is how y'all were taught a hexagon looks when you were a kid. Now, they didn't mark it all up and everything. But Y'all got taught that's what hexagons look like. Okay, well, yeah, 1, 2, 3, 4, 5, 6. But that is a hexagon too. And like it drives me nuts that y'all were taught that octagons or stop signs look like octagons. Like all octagons look like a stop sign. And no, regular octagons look like a stop sign. Okay? So this one, here's a hexagon that's neither equiangular nor equilateral. Here's a hexagon that's equiangular. And if you're like, well, how do we know that all those are 120 degrees? Well, if it's equiangular and there's 6 sides, then 2 less than that, it would have formed 4 triangles when I drew in my diagonals. So 32, that'd give me 720 degrees total, but there's 6 of them, which meant each one was 120 degrees. Here's an example of an equilateral hexagon, but these angles are definitely not the same size. But here's a regular hexagon. So every single angle would be 120 degrees big, the interior angles that is, and all the sides are going to be the same length. Okay, now here's where these are my favorite type problems. A regular polygon has 12 sides. Therefore, we call it a dodecagon. Find the measure of each interior angle. All right, so there's 2 ways to go about this. Here's the way most people teach it. There's 12 sides, so 1, 2, 3, 4, let's just say it's regular. I'm not going to draw all 12 sides because that'd be hard, but you know, there's going to be, here's what's going on. I'm looking for how big each of these is. So if there's 12 sides, that means if I picked a vertex, drew in all the diagonals, I'd create 10 triangles. So I know there's 1,800 degrees total. If I take that 1,800 degrees and divide it up 12 at a time, each one of those angles is 150 degrees. Okay, so, but I did it kind of in pieces. Most people would just, well, I don't know, most people probably do it in pieces. But I think it'd be more efficient just to say I was doing that. All right, and there is nothing wrong with that. However, I know you, and you think like I do, why are we going to beat around the bush when we could do this much quicker? So, what if I just took a side and extended it and created myself an exterior angle? Well, the beauty of the exterior angles of these convex polygons is that they always add up to 360 degrees, and there's still going to be 12 of them because there's 12 sides to this thing. That makes each of these 30 degrees, which, according to the linear pair postulate, because there sits a line, that makes that 150 degrees. And you better believe that is the way I'm going to do it. So I'm not going to do it the other way. Right here, find the value of each variable. So let's see what we've got. Here's a bunch of exterior angles. I know that they add up to 360 degrees every time. I've got a linear pair right here. So if that's 88 degrees, let's see, what's that going to leave? 92 degrees on the other side. So then I've got that. I know that the 90 plus the 70 plus D plus 92 makes 360. So let's see, this 160, 260 come up 8 short, so 252 plus D makes 360. You know what I wish I'd done? It doesn't matter. Let's see, subtract 252, 108. So this is 108 degrees. Here's what here's what I wish I'd done. Subtract 90 from both sides. Subtract 70 from both sides. And then I could just subtract 92 from 200, and that would have been much quicker. I like that way better. All right, we've got linear pairs right here. So if this is 108 degrees, what's that going to leave me with? 72 degrees. On that side, you got 180 there. It's going to leave me 110, and there's going to be a right angle. Okay, so if you're making your list, what do we figure out? Now, I need degree signs on these because there's no degree signs. So A is 90 degrees, B is 110 degrees, C is 72 degrees, D was 108 degrees, and E was 92 degrees. Okay, All right, find the measure of one exterior angle of a regular decagon. So we know there's 10 sides. All these are the same measure. These are all the same length. I just draw a few of them instead of trying to draw the whole thing. They're wanting to know how big that is. Well, I know the exteriors add up 360. I know there's 10 of them. That is a 36-degree angle. Okay. Find the measure of one interior angle of a regular decagon. Well, I'm not doing any extra work. I know that's 36 degrees. Here's 180. I know this is 144 degrees because that is absolutely the fastest way of doing it. Now, could I do it another way? Sure. If there's 10 sides, and like some people like to actually write the 10 minus 2 times 180, and then you would have 10 sides that we'd have to split it up into, oops, and then we could go 10 into that goes 18, so 8 times 18, 64 carries 6. There's that same 144 degrees. But that was already obviously just jumping out at us. Okay, all right, so here's what it says. You can memorize formulas, but as you probably guess, I seldomly use a formula. So here's how a lot of people do this because they memorize it. What's the measure of each interior angle of a regular polygon? So they'll take the number of sides, they'll subtract 2, they'll times that by 180 because that's the sum of the interior angles. They'll divide by the number of sides because there's the same number of vertices as there are sides. And that gets, that's one way. You'll also see it, another way people write this formula is they'll actually take and distribute the 180. And then for this part, 180 n over n, that's 180. And then minus 360 over n. You'll see people do that too. But, and that's actually what we're doing if you like a formula. Because we're saying, we're figuring out, okay, how big is this angle? Well, that's 360 divided by however many sides there are. And then we're subtracting that from 180 for that linear pair. So you can look at it a couple different ways. But again, I seldomly use that formula. I'll use it every once in a while if I have to work backwards. Like they tell me something about how many sides if this happens, and sometimes I might want to do that, but not real often. This one is just, okay, exteriors always add up to 360. There's insides, so divide it up. Same number of angles as there are sides, so we divide by the number of sides. Example 6, let's see what we got here. The measure of each exterior angle of a regular polygon. Okay, so I'm not going to worry about how many sides there are. I don't know. I'm just going to draw enough. Here's an exterior. We're saying that's 20 degrees. I know that's 160 degrees. How many sides does it have? Okay, well, here's the 2 ways you could do it. Here's the fast way. I know that there's 360 degrees getting divided up 20 degrees at a time. So there's going to be 18 of those, which implies that there are 18 sides. Okay, that's personally what I would do. Some people would use this formula and say, okay, that's the measure of 1. I know that equals 20. They'd cross multiply. Of course, we could have left the degrees off because we could have divided both sides by degrees. And that gets them 18. Some people are just gluttons for punishment, and they would say, the number of sides, take away 2. If you times that by 180 and divide by the number of sides, it'll give me that 160 degrees. So, and I'm going to divide both sides by degrees so I don't have to keep up with it. That gets me n minus 2 times 180 is 160 n. So this gets me 180 n minus 360 makes 160 n. There's going to be 20 n is 360. N is 18. Like, why in the world you wouldn't do this? I don't understand. So my guess is you're going to do that. Let's see what we got on example 7. If the measure of each interior angle, okay, so however big they are, so it's regular, so don't know how many sides, but I know that all these are 168 degrees. again, we could go the number of sides minus 2 times 180 divided by the number of sides. I know that's 168 degrees. Let's solve it for n. But we could also just do this. Hey, look, that's 12 degrees. I know there's 360 degrees. I'm dividing it up 12 degrees at a time. That means there's 30 sides. This is the math team way to do it. We don't waste a bunch of time doing a bunch of crap that we don't need to do. All right. Oh, we're getting close. This is a long set of notes. How much? Just through example 8? Yeah, okay. So what time have I got? 5:36. I might have to finish this in the morning. At 6 o'clock tonight, I've got to meet my high school classmates at Burrito Jalisco. I don't know how do you say it. Jalisco? I think it's Jalisco. Anyway, for supper, we call it our third Thursday supper club, where every third Thursday of the month we get together. However, we've been doing this for about 2 years now, and the longer it goes on, the less people show up because I think they were just like, well, it'll happen again next month. So we think we've been doing it too often. So I think we're going to change to every 5th Saturday, because then it's only every 3 or 4 months, or maybe even it might even stretch to like 5 months in between. And that makes it more special, and we think people will show up more. Plus, Thursday nights are hard for folks who have to work late. Like, I've got one person who would come every time, but he works for UPS, and he doesn't usually even get off till 7 o'clock on Thursday nights. So anyway, I just wasted like 2 minutes right there telling you why I'm probably going to have to... I can probably be a minute or two late. There's no reason for me to stop until I'm done. All right. So we're going to talk about how to find how many diagonals you can draw. You'll like this. So how many diagonals can you draw from one vertex? So let's just pick a vertex, draw them in. All right. So if there's 4 sides, I could just, from that one vertex, I can just draw one diagonal. Okay. How many total diagonals, though? Okay, so pick a corner. There's a diagonal. Pick another corner. There's a diagonal. Now, when we get to that last 2 corners, like this one, you've already drawn that diagonal in. This one, you've already drawn that diagonal in. So if there's 4, oops, I left the S off right there. If there's 4 sides and I'm doing total diagonals, then there's 2 diagonals that I could draw in. Okay? All right, so let's see how many sides we got here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have an octagon. Why did it not turn to an eraser like I wanted it to? All right, so we're going to figure this out. So from one vertex, you pick your one vertex. Okay, remember, you can't connect it to the 2 next to the 2 vertices beside it, because that's a side. But we can connect it here, 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 and here. Now, we've already done this. If there were 8 sides, like when we were talking about what do the interior angles add up to, we would say, oh, with 8 sides, I can create 6 triangles. I'm not looking at the triangles anymore. I'm looking at those actual diagonals. So I just created 1, 2, 3, 4, 5 diagonals from that one vertex. Okay, and then right here, well, what if we drew them all? So let's start. Okay, from that one, I can draw 5. 3, that looks gross right there. Pretend like, put a big, okay, so I made 5 right there. Let's switch colors. Let's come to the one next to it. That I could draw in 1, 2, 3, 4, 5 from there. All right. Now, some people will go, oh, it's 5 times 8. It is not, because when you get to the next vertex, one of those diagonals, this one right here, is already drawn. Don't draw it again. Let's get rid of it. What color? I'm doing green. Okay. So I'm not going to draw that one, but I could draw in, hang on, I'm going to turn this where I don't mess it up. I could draw in this one. So 1, 2, 3. I could draw in 4 more. All right, let's go black. Now from here, 2 of them have already been drawn, so I'll draw in the other 3. So 1, 2, 3. So I put 3 extras here. Let's do this blue color. So I've got 1, 2, 3 of them already drawn, so that leaves 2 more I can add in. When I get to, what color have I not done? Haven't done purple. Let's do a purple. All right, it's got 1, 2, 3, 4 of them already drawn. There's only 1 extra I can add in. And then when I get to here, 1, 2, 3, 4, 5, all 5 are there. When I get to this corner, 1, 2, 3, 4, 5, all 5 are there. So there's nothing to add for those. We've already had them. So our total diagonals we'd have 5, 5, 4, 3, 2, 1. So there's 10, 17, 3 more. 20 total diagonals. Okay? All right. Now this is always fun for me. This is a huge, not huge, who's not the right word. It is a very common ACT question. And SAT, because you're probably going to, I would say you're definitely going to be taking both. But they love to ask this on standardized tests because they know that a kid can sit here and draw this and count them up and find them all. But that takes a while. And usually the diagrams are very small, and because the reason I know this is on there is because I used to give the ACT test all the time, and it was the easiest money ever. You just basically have to sit in a quiet room for 4 hours and you make like $150. Like, sign me up. But I would watch kids at least, I would say, 1 out of every 3 tests sit here drawing this thing. And they'd give them stuff like 20 sides, and they would waste 10 minutes trying to count up all these stinking diagonals. We are not going to count them up. We did this first time, so you can see exactly what's going on. But we're going to figure out the formula for it, okay? So let's say I've got just n sides. 1, 2, 3, 4, well, I don't know how many are. There's just n of them. And you're picking a random vertex. How many different diagonals can you draw from that vertex? Well, remember what happened up here when we had our 8 sides. Let's do one with 6. 1, 2, 3, 4, 5, 6. What you're doing to create the diagonals is you're picking another vertex to connect it to. So there's 1, there's 1, and there's 1. But the reason you're connected to those, so this vertex, and this vertex. So this is where we maybe say we started from. We don't connect it to the one right next to it, that's a side. We don't connect it to the one right next to it here, that's a side. And we don't connect it to itself. So what you're doing is, like right here, there were 6 sides. We knocked 3 of the vertices out of it because it's itself and the 2 beside it, which would create sides. So if there's n sides, well, that means there's n vertices. And wherever you're starting, you can't connect it to yourself or the 2 right beside you, but you can connect it to everything else. So how many diagonals can we create from just one vertex? N minus 3. Okay? All right, now this next part, you've done a tiny little bit of this, but I'm just going to give you a crash course in, and maybe we probably should. Hang on, I'm going to write myself a note. I need to give you a little crash course in permutations and combinations. Combinations. So permutations and combinations. So that means I'll have to round up some new notes. But I want you need to look at all that kind of stuff. And it may be part of the statistics that's in geometry anyhow. I haven't looked at all that part because so far we're just going through the geometry from my prep school in Indianapolis. But the state of Alabama, in honors geometry, you also have to do some statistics. And I'm thinking this might be where they bring in permutations and combinations so it wouldn't come from out of nowhere and I could just go ahead and teach it to you while we're doing this kind of stuff. But here's a good example. Let's say there's 8 people in a race. And I want to know how many different ways we can hand out first and second place. Okay, so let's say it's person A, B, C, D, E, F. How many letters is that? 6. G, H. There's 8 people. So we've got that, like, A could come in first and B could come in second. Or A could come in first and C could come in second. Or A, D, A, E, A, F, A-G-A-H. And then we start out with the B's. Okay, so B could come in first. And then A could come in second. And C could come in second. Or B could come in first. Like, here's the thing, though. I don't want to sit here and do this. Like, this is very aggravating. So here's the way I do it. Here's first place. Here's second place. Out of these 8 people, how many of them could win the race? All 8. Any of the 8 could win. Once you decide who wins, how many are left to come in second? 7. And then you multiply those together. So there are 56 different ways you can hand out first and second. Now, that's different if you said, okay, let's say there's 8 people. And I said, how many handshakes are possible? Well, there's still, like, you got to pick the 2 people to shake hands. So there's 8 people that you could pick from to be the first person to shake hands. 7 to pick from to be the second person to shake hands. However, it doesn't matter. Like, A, B, and B, A, that's 2 different things. One got first place, one got second. Like, it's 2 different medals. But if you did this and this, and just shaking hands, nobody cares who sticks their hand out first. It's still the same handshake. So what we do is we go, okay, well, there's 2 people shaking hands. Out of those 2 people, how many could have been the first one to extend a hand? 2, which left 1 to pick from second. So you're really just doing 8 times 7 divided by 2 because the order didn't matter, and that's called a combination. So there's just 28 different ways that you can pick people to shake hands. Okay, so what's happening here? We're doing the same idea. I've got to pick a diagonal. So if there's n sides, there's n diagonals. All right, how many could I attach it to? N minus 3. Oops, there we go. But it doesn't matter, like if we draw in some random polygon, it doesn't matter if I go from point A to point B or if I go from point B to point A. It's the same diagonal, so we divide it in half because, well, technically we're doing like I did. We're picking out of those 2 points that I chose. 2 of them could have been picked first. That left 1. So what the formula is it's the number of sides multiplied by 3 less than the number of sides, and then you half it. Like that's a super, super big. So like the one that we just did up here, how many sides was it? 8 sides? Take your 8 sides. I've got 5 vertices I could connect it to, but I only want to count half of those because I don't want to double count the same diagonal. And there's that 20, which is so much easier. Okay. Last example. What time am I doing? 5:48. Ooh, if I get through this, I might could actually make it on time. So the interior angles of a regular polygon, or the interior angle of a regular polygon, again, don't know how many sides there are, so I'm just making up something. That should look like a corner, and it really doesn't. Let's work up here at this one that looks the best. So the interior angle of a regular polygon is 3 times as big as its exterior angle. So I'm going to extend and say, okay, that's x degrees. Here's 3x degrees. How many sides, so we're hunting for n, does this polygon have? How many total diagonals can you draw? All right, well, the thing that I know is that that's a linear pair, x and 3x. So those 2 put together have to add up to 180. So 2x is 90, x has to be 45. All right, so I know this is a 45-degree angle. Now, that also means this is 135 degrees, but I don't really care so much there. I like this one. So I know there's 360 degrees total, and I'm dividing it up 45 degrees at a time. So that's going to be 8. So that means that there's 8 of those vertices, which means there's 8 sides. If there's 8 sides, I'm going to let n be 8. And then for the total, how many sides does it have? Okay, 8. How many total diagonals? Take the number of sides, multiply it by 3 less, and half it. So there's 20 total diagonals that we could draw in. And I don't know about you, but I just had a really good time working all these problems. And I'm going to go now because it's almost 6 o'clock, and I think I can still make it because we're just going up here to the burrito place at about 18th Street. All right. I hope you enjoyed that.